Okay, hello everybody. This is lecture 21 for thermodynamics, ME3331. Yeah, as you notice today, I have a new feature. I've just put up a video so you can see me. I don't know how whether that's gonna be valuable or not, but essentially that's that way you know that I'm a human and I'm here. So that's a new feature of my video lectures, and hopefully it'll go well. So I don't have an exciting background for you or anything. I'm just sitting here in my room figuring this out. So today I'm going to be giving a lecture continuing chapter 4 on control volumes. As you can see here in the slide, we are going to today talk a little bit about heat exchangers and about throttling and about system integration. So integrating these different parts together for steady state systems. Okay. So I have some announcements here, some general announcements that I've written down. So the first thing is that for survey 16, I'm going to go over the results here. Let me just look at the results for survey 16, and I was looking at it. One thing becomes immediately clear as you look at the survey 16 results here is that you have a big distribution of different responses. Okay. When we do this in the class, the people kind of talk to each other and are able to answer these. I would maybe encourage you guys to use chatting functions or something like that to discuss the survey question. You know, try to do that with somebody else. Maybe you're using chat with somebody or somehow communicate with other people to get these survey questions, because I'd like to get these to converge on the right answer eventually. I think that'd be really good. Okay, so let's look at this. Let's look at this result here. You can see, yeah. So the question is, what steady state device extracts work from a high pressure fluid? Okay, so the key things here are extracts work. So that means you're something that's going to do work from a fluid. Okay, so this would imply, so you're going to something that's going to have a work output. That'd be a positive work output from a high pressure fluid. Okay, so a pump is not right. Essentially, pump is something that you put in, you put work in to raise the pressure of a fluid. So low pressure fluid goes in and liquid, mostly for pumps, and then out comes high pressure fluid. Okay, compressor, same deal, but mostly we use the term compressor for gases. Okay, so yeah, so not totally right here, guys. So turbine is the correct answer. So at least we got the correct answer there. So a turbine, as we mentioned, takes takes a high pressure fluid and then extracts work by decreasing the pressure across some sort of like turbine blades or something like that. Okay. Diffuser, one person said diffuser. Diffuser doesn't do anything with work. So a diffuser has a smaller area and then opens up to a bigger area, right? So that's not correct either. Okay, so those of you who answered these things, which it looks like most of you were able to, there were some issues with people getting on because there was some too many people using the system. I think this was just a matter of the whole university's teaching system being overloaded. So I'm sorry about that. Hopefully tomorrow it'll be better. So same deal will happen on Friday. So go to the next one. Here, let's go to the next question. So the next question here is for an ideal gas with constant specific heats, which of one of the following is always true? So the key here is always, right? So du equals CVDT is not right. So the first one, this isn't correct because this would be du equals CVDT, the constant volume specific heat, as we went through in class. So please review that one. This is the correct answer. So at least people are getting the correct answer as the most frequent answer. So this is good. So we have dH is equal to CPDT. And that's true. So this is the definition. So the definition is dH dt equals CP. And so that's the correct answer for constant specific heat. And if it wasn't constant, it would be an integral, right? Because it'd be the integral Cp dt, because Cp would be changing with temperature. When somebody asked me a question during my office hours yesterday, essentially, the question was, if you have an ideal gas problem, when do you get to assume that you have constant specific heats and use the specific heat? Essentially, the answer is when the problem tells you to do it. Okay, so not anytime, but just when the problem says assume constant specific heats, then you can look up the specific heat in the table, or you can use the value that's given in the problem, okay? So that's the answer there. So Q equals CBDT, this might be true, not always true. So this is a first law expression. So Q, so the heat transfer could be delta H. Same thing here. The work could equal CPDT. In fact, like for an air turbine, a gas turbine, for instance, or a gas compressor, this might be the case, but not always true. So, okay. As I said in the just as we did before, these surveys are not graded, so don't worry about it. But I would like you to get the correct answer and understand what the correct answer is. So, interesting result here for problem, for these now that we're doing them independently and remotely. Okay. Let's see other things that I have on my list here. So YouTube link. So another student recommended that I put these video recordings on YouTube as opposed to directly as a MOV file on Canvas. Okay. Yeah, so I'm tried both, and I'm going to try both with this lecture too, and we'll see which one's better. Maybe if you can give me some feedback, I would appreciate that, and let me know which one works better. So YouTube, I might get a higher res video, and you might like that better. So I don't know, it could work for you better. So I'll just put that up for lecture 21. Also, the discussion section. Hopefully that went well today. That was this is Thursday. I'm recording this. So hopefully that went well. I wanted our TAs to use the Zoom link here. So if you look here at Canvas, let's see. If you look at Canvas, I'm going to do a little thing here. Okay, so if you look at Canvas and you look now, I've added this new section, this new piece called Zoom. So this new heading, and you can see all of my office hours are in here. I don't see the discussions in here. So I'm a little bit concerned that maybe when Ollie did this, he didn't put that in, but I would like to also see that those discussion sections are in here as well, and maybe the other office hours as well, so you can just go in here and go click and join the meeting, okay? Well, this one's for me, I'm a host, but if I was to look at the student view, essentially if I look at the student view, see if I can see it. We go home, or go here. Let's see if I go here and then go to student view, I should be able to show you what it looks like for you. Okay, here's what it looks like for you. Go to Zoom, so you could say join, right? So if this was the office hours, recurring office hours I have scheduled in here for myself, you can just go here. I'm available for 2 hours every Wednesday from 1 till 3. Okay, so you can ask me any questions about the problems, figure out how to use Zoom, ask me questions about anything, essentially. I'm here sitting in this room waiting for you to call me. I'm not lonely, but it's fun to have some dialogue with you guys because we don't get to sit in class together anymore. So please, if you have questions, let me know. We can also schedule impromptu Zoom meetings too if you want, or even those kinds of things. So, all right, reset. So I'm going to leave the student view here. All right, so now let's get to the material. I think that's it for my general announcements. So let's go to the material. So go back here to my slides. Okay, so today I'm going to talk about 2 new control volume things. The first is called the heat exchanger, and we're going to talk about heat exchangers first. So there are 2 different kinds of heat exchangers that we have. Okay, both of which can be analyzed as a steady state control volume. The first is direct contact heat exchanger, which you see here in the upper left. In this case, you have fluid coming in one side and a fluid coming in another side, and they mix together in some sort of box, and they directly mix, okay? And then out comes a mixture of the 2 things. Now, this can be analyzed just as well, like if you had, say, water coming in here and steam coming in here and some 2-phase steam coming out or something like that. You could do that, or hot air, cold air. You can have 2 different fluids possibly, but we weren't going to get into mixing, chemical mixing in this class, so we don't have to worry about that. So here, there's the other one. We have an indirect heat exchanger. This one's called tube within tube. We call this indirect contact heat exchanger. Okay, so this means that essentially you have one fluid in a tube, for instance, in this case, and another in an annular tube wrapped around the outside of it, and then you have the exhaust. Okay, so the gas or liquid as cerium is separated from another gas or liquid by a wall through which energy is conducted. Okay, Heat transfer occurs from the hot stream to the cold stream as the stream flows in opposite directions. Okay, so then we have a situation where we have heat being transferred from one side to the other, and you have a hot side and a cold side usually in a heat exchanger. We can do an example. So the next thing to do is to look at how the first law breaks down. So for the mass continuity essentially, or the mass conservation, obviously the mass is conserved on the blue side here, and the mass is conserved here. Just like here, the sum of the mass coming in is equal to the sum of the mass coming out. So that's pretty trivial, I think, and pretty easy to understand. Then the next slide here shows essentially for heat exchanger, for the modeling. So in the first law, you have, in this case, you have the heat term going away because, well, we don't have to actually. You don't have to have an adiabatic. If you can neglect the heat or not is kind of up to the problem. You could actually have heat loss from a heat exchanger. Oftentimes you do. So in this case, say we go to 0, work goes to 0. Kinetic and potential energies, again, we're going to neglect these. We're not interested in velocity for heat exchanger. The idea is to take a hot fluid and heat a cold fluid, or vice versa. So that's not really something we're that interested in doing. So if the kinetic energies of the flowing streams are negligible, then these drop out, then the kinetic potential energies drop out, and then what you're left with is if you have an adiabatic system, that is, if the heat transfer of the surroundings is negligible, we call that adiabatic. Remember that, okay? Then you end up having something that looks like this. So the sum of the mass flow in is equal to the sum of the mass flow out times its enthalpy. I'm sorry, sum of the mass flow in times enthalpy equals the sum of the mass flow out times its enthalpy. Okay, so that's the general idea with the first law. So it's pretty simple actually, not that difficult to go through. So let's do our first example of the lecture today. So let's look here at a heat exchanger example. So here, let's see, steam at a pressure of 0.8 bar and a quality of, 93.2%, so I'll move myself here, in a shell and tube heat exchanger, which is shell and tube. When I say shell and tube heat exchanger, I mean this, right? Shell and tube, tube within a tube, shell and tube, it means the same thing, okay? Where it condenses on the outside of the tubes through which cooling water flows, exiting as a saturated liquid at 0.08 bar, and the mass flow rate of the condensing steam is 3.4 times 10 to the 5th kilograms per hour. Cooling water enters the tubes at 15 C and exits at 35 C with negligible change in pressure. Negligible change in pressure means there's no pressure drop through the tubes, okay? Neglecting straight heat transfer, so this means adiabatic, okay? Make sure you read the problem. And ignoring kinetic and potential energy effects, determine the mass flow rate of the cooling water in kilograms per hour for steady state operation. All right, it's given us all the keywords here that we need, right? All the keywords that we need to solve this thing. I'm gonna do this. I move my mouse here. I'm gonna do this here. I have it right there. Okay, great. So now we can do this problem. So steam at a pressure of 0.80. So let's just do it here. So so make sure I have my pen working right. Good. Okay. So let's just so say known. It's a heat exchanger. For steam. With properties given. Okay, we need to find. We'll just say find the m dot of cooling water. Okay, great. So let's move on to the problem. So let's make a schematic. So let's see. I think we already had this, but let me just do it again. Here, I'm going to do a little bit smaller pen here so I can get it looking better. So let's see. We have a box heat exchanger. It's a shell and tube heat exchanger. So essentially, we'll call this the shell side, and then you're going to have stuff coming out. We'll call this state 1 and state 2. Okay, this is the shell side. and then there's a tube side. So there's a tube that's coming in here, and it's kind of like going in like this. So we'll say this is coming in, we'll call this 0.3, and going out, we'll call this 0.4. Okay, now, of course, as we always have to do, we have to make our boundary for control volume. So let's do that here. Okay, so this is our control volume, and we'll label our system control volume. Okay, good. So we've done that. Now, let's see. Let's put in what we know. We know that P1 equals 0.08 bar. We know that X1, the quality, equals 0.932. We know that M dot 1 is equal to 3.4 times 10 to the, 10 to the 5th? That's a lot, kilograms per hour. That's a lot of flow. Okay, so let's see. We know that state 2, this is sat liquid, and there's negligible pressure drop, right? So if we think about this on the pressure like this, so the quality here is pretty high. So if we just think about what this looks like in a TV diagram, remember this? I hope you remember this. Okay, so what we got here is that this is state 2 and this is state 1. Okay, on the shell side, it looks like on the shell side we've got cooling water. So we just got cooling water, which is always over here in this region, and the pressure is negligible. So we don't even really need to know. We just need to know this. So we know T3 is equal to T3. What do we have? T3 is equal to 15 degrees C, and T4 is equal to 35 degrees C. And we know this is water, so so this is on the tube side. So you have essentially steam flashing over these tubes. On the tube side, this is water, and this is steam, right? Okay, we'll just say equals P2. Okay, does that make sense? Hopefully. Now, okay, so now we have the diagram and stuff made. We'll just do some analysis here. We're kind of given everything we need. We might have to look some stuff up in a table, okay? But that's all right. Well, we can do that. We have the table here. All right. So now let's look here. So let's look at the first law. Okay. So for the first law, essentially what we're gonna do is we're gonna go 0 equals Q dot minus W dot plus M dot 1 times H1 minus H2, because the mass flow is not changing, but we have to take, so M dot, we'll just say M dot 1 equals M dot 2, and M dot 3 equals M dot 4. Okay, because as I said before, there's no mixing of these streams. It's an indirect heat exchanger. And then we're just going to neglect potential and kinetic energy. Oh, shoot. Guess what I forgot? I forgot my assumptions. I always have to make the assumptions. Let's see. Where am I going to put them? Let's see. Well, let's do this, and I'll put my assumptions in. Then we just have to, let's just finish off my thought here. So M dot 3 H. I got ahead of myself. 3 minus H4. Okay. Here we go. So let's put the assumptions down here in another box, as if we had to remember to do them ahead of time. Okay, so one assumption is that we have steady state control volume. 2, we're assuming here that we have a let's see, no work equals 0. It's adiabatic equals 0. No KE, delta KE, or delta PE. Okay, we don't have any of those things. And then we're also assuming here at the very bottom of my thing here, H equal is equal to H F. Oops, I am at the very bottom of T. Meaning that essentially when we're looking at, this is an F. Okay. Essentially, when we're looking at using the H value from the table, we're going to use the HF value, okay, for the liquid. So essentially, it's only a function of temperature, not of pressure, like we've talked about a few times. So hopefully, you get that. Okay. So example 1 continued. To zoom up a little bit here. Whoa. Okay. Example 1 continued. Now let's see. So then, if we just solve, rearrange. So just rearrange the equation. You get m dot 3 equals m dot 1 times h1 minus h2 all over h4 minus h3. Okay. So that's fine. We can handle that pretty easy. So now we need to know, where are we at here. So we have 0.8. So if we just think about P1 and 2, P1 equals P2 equals 0.08 bar. We're going to look up at table A3. So let's just do that. So let's just do that here, because you may not remember how to look things up in the table. So let's do it. Let's see, table A3, saturated water pressure table. Oh, goody for us that we have this. Let's zoom up on it. Get the right zoom for the right thing here. Okay, you can see here we definitely have 0.08 bar. Okay, so now if we just go over, let me move myself down here. So 0.08 bar, we need the H's, right? That's what we need. We need the H's. So here 0.08 is right here, and I'm just going to write it down in my notes here, like I usually do in the class, and we'll just say that H1 is equal to H F, let's see, plus x1 hf minus hg, which is equal to hf plus x1 hfg, because it's given to us in this table. You see, hfg is given right there. Okay, so that's cool. So 0.8 is right here, so we just need hf is 173.88. So h1 equals 173.88 plus 0.932. Oh, you're seeing my email come through. Isn't that nice? Okay. Times HFG. So HFG is given right here. It's 2403.1. 2403.1. Okay, and this, if we do the math here, I have it written a separate piece here. It is 2413.6 kilojoules per kilogram. Okay, no interpolation required. Great. Okay, so we also know that P2 is equal to 0.08, and H2 is equal to H. Oh, get rid of that. Is HF at 0.08. So that is just what we had written down. So that is 146, 0.08, and that is 173.88. Okay, so now let's look at H. We need H. All right, I'm going back here. So you're not seeing it yet, but here I've written it all down here. Okay, so now we're going to go back in H3. We have to go to the temperature table. So A2, table A2. All right, so table A2. Let's go to table A2. Let's see, table A2. Let's go up here, table 2. So we have, what are the temperatures again? We have, let's see, 30, 15, and 35. So 15 is here, and we're looking for HF. So equals HF at 15 degrees C, and H4 equals HF at, what is it, for 35? 35. Okay, so let's look it up here. So let's see. We look it up here in the temperature table. So 15 is 62.99. I'm writing these down. You'll see them here in a second. Kilojoules per kilogram. And for the next one, it's at 35. So 35 is over here, and that is, oops, it's this column right here. So it's 146.68. 146.68 kilojoules per kilogram. Okay. All right. So now what we have to do is go back here. All right. So now you can see this again. So let's, oops, sorry about that. Okay. So now let's go over here and let's just finish this off. I'll move my camera back up to the top. And then we just finished this guy here. So all we have to do is then plug into our equation. So m dot 3 is equal to 3.4 times 10 to the 5th kilograms per second times, the kilograms per hour. Kilograms per hour, 2413.6 minus 177.8. Oops, 170. Let's see, 173.88 divided by the difference here, which is H4 minus H3, which is 146.68 minus 62.99. Okay, and then this ends up giving us an answer of 9.06 times 10 to the 6 kilograms per hour. All right, and this is our answer. Okay, not too bad, right? All right, so we can get this done pretty easily. So heat exchanger, one thing to note about a heat exchanger, I'll show you here. In the case of a heat exchanger, you have, in this case, you notice you have flow going through one side on the outside. This is the shell side going this direction and flow going this side. Sometimes we call that a counter flow heat exchanger, okay? And sometimes they're going together and we call that a co-flow heat exchanger. You're gonna learn more about that when you get into your heat transfer class, 3333. But anyways, it's just a little guess. And if we get into, when we do second law, we'll start thinking about the entropy differences and the differences in sort of efficiency of heat exchangers using counterflow versus co-flow. All right, but let's not worry about that now. Let's just move on to the next thing here. Where are we at? Okay, good. We have almost 30 minutes, so we have time to do a little bit more here. Let's do throttling. Okay, so next thing we're going to do is throttling. So a throttling device is a device that achieves significant reduction in pressure by introducing a restriction into a line through which gas or liquid flows. Means to introduce the restriction to include partially open valve or a porous plug, or if you have a clogged pipe, for example, so there's a lot of different kinds of throttling that might occur. Pretty much what it means is that there's a restriction in a flow. Okay, throttling just means that you drop pressure across something in a gas. So everybody's used to, say, for instance, a water faucet. You know, in your sink, when you turn the water faucet on, essentially you've got pressure in your water line at 28 or 60 psi or whatever it is in your water pressure is in your house, and that water pressure then essentially is dropped across a valve, and that valve is the thing that you turn the water on, and then it drops to atmospheric pressure when the water jet comes out of the faucet, right? So that drops to atmospheric pressure. So that's what we mean essentially by throttling. It's through that valve that you get the throttling process where you drop pressure. And we can analyze that from a thermodynamics perspective, right? So we can develop our equations for that, and that's essentially done here. So watch this. So here, throttling device. So any throttling device essentially is a really simple first law analysis, right? Because obviously the mass flow in is the mass flow out, and that's also simple. So essentially what we got is work of the control volume is 0. The change in kinetic energy, again, usually 0. Sometimes you assume like right in the throat of the nozzle, like for right in this little spot right there, right by the valve opening, you might have velocity. But if we take our control volume, this is the beautiful thing about control volume. You just take it far away from where all the like crazy action is going on. Like there's like velocity coming in here and squirting out of this hole and all that stuff. Don't worry about it. Fully developed flow on either side. Just take your control volume sufficiently far enough away from those things and you're fine. Okay, so no big deal. All right, so let's see here. Now we have H2 equals H1 is the eventual equation if we assume that this is an adiabatic problem. Okay, so adiabatic, we just generally assume that this is an adiabatic if there's no heat loss. So sometimes you can, sometimes you can't. It just depends on the problem, as I've said before. So it just depends on what's going on. Okay, so now let's see what's going on here. There's a throttling example. Okay, so we're ready. We're just ready to take on an example here. So let's just do it. All right, so this is example 2 for the class. So let's just go here, and I'm gonna get us an example again. So here we are. Yeah, so just keep on moving myself around here. So a horizontal constant diameter pipe with buildup of debris. So buildup of debris. So that means like a clogged pipe. Shown in the figure, which I showed on the slide. You can look at in the slide. I posted the new slides recently. Air, modeled as an ideal gas, enters at 320-900 kPa with a velocity of 30 meters per second and exits at 305. Okay, assuming steady state and neglecting stray heat transfer, determined for the air exiting the pipe, the velocity, and the pressure. Okay, so no problem. We can do this. This is really no problem whatsoever. We can take care of this problem. So let's do it. So here we have to write down everything we know. So let's just get going here. So known. We have a pipe with airflow and debris. Okay, what we need to find in this problem is the exit. Find the exit velocity, so V2 we'll call it, and the pressure P2. Okay, because as I said, a throttling valve decreases pressure. You just heard the doorbell and my dog barking, so you know I'm still at home. Okay. Okay. So let's see. The way we're gonna do this is okay. First, let's make a diagram. So the diagram looks like this. We have a pipe. So I draw a pipe like this. You know, you can just, I don't know. Oh, it's going to take my whole line away. All right, it looks like this. All right, I'm getting too picky. All right, so now we have a buildup of some sort. So inside this pipe, there's some stuff. Oops, got my line back here. And there's some stuff in here. Some junk. Okay. There's some junk inside the pipe. Debris. All right. Okay. So now we have to have air coming in. So we have. Oops. Let's just undo that. Put my thing back there. Okay. So we have air coming in and air leaving. So we're gonna define our control volume here. As I said, we wouldn't put our control volume here. No, don't do that, right? Because what's the point of that? It's all unknown and weird in there. We're gonna take the flow where the control volume, where the flow is uniform, okay? All right, get rid of that. Now, all right, so now we have, we're gonna call this point 1 and call this point 2, okay? All right, exiting and leaving. We're gonna make some assumptions. First, 1, we're gonna assume ideal gas. 2, we're going to assume this is steady state. Okay, and then anything else we got to do? I guess we're going to assume 3. We're going to say, we're given velocity, so we're going to say no delta PE, right? No, we're going to say, does it say anything? This is interesting. Neglecting stray heat transfer. There you go. So we're going to assume this is an adiabatic. So we're going to know Q dot, and we're going to assume here that this is also yeah, I got this one. Okay. No Q dot, but we are going to assume that we have, and of course, no work dot equals 0. All right. So here's our analysis. And it looks like this might be the last one of the day. I don't know. We'll see, because the other problem is kind of long. But that's okay. We'll see what we can get through here. Heat exchangers and throttles might be good enough for today. All right, so here we go. Here's the analysis. Then essentially what we've got here is 0 equals Q dot minus W dot plus M dot H1 minus H2. Oops. Let's go here. I forgot that we have to take into account our velocity term. Plus V1 squared minus V2 squared over 2. Okay, we got to do that. We're neglecting potential energy, so that the gravity term goes away. All right, so here we are, the first law. So this is first law. You got to be getting sick of this by now, but we got a couple more classes of this. Get used to it. Okay, so let's make this a little neater here. All right, good. All right, so now, yeah, this goes to 0, but we're going to keep that. So that goes to 0, no Q dot, it goes to 0. And so what we're left here is essentially H1 minus H2 plus V1 squared minus V2 squared over 2. And so then we'll just solve this for, equals 0. So V2 then equals the square root of V1 squared plus 2H1 minus H2. Okay, no problem there. And then, let's see. We did not say specific heats, so we cannot assume constant specific heats, okay? CP equals constant, because it's not said. So we're going to use the tables instead. All right, so to save time here, A20, so this is table, if we look up table A22, we can find out that as we know that the temperature here is given, so 320 and 305. So this is, I'm just going to say T1 equals 320 K, and T2 is equal to 305. So if we know that H for an ideal gas is only a function of temperature, right? Remember that. H for an ideal gas and U for an ideal gas is only a function of temperature, okay? Good to know. All right, so then we know H1, if you look up table A22, we can just look, I'll just tell you what it is. It's 320.29 kilojoules per kilogram. And H2 is equal to 305.22 kilojoules per kilogram. Okay, so that we know that already, though that's good. So if we plug things in, I'm just going to the next page here. So example 2 continued. Give us a little more zoom up here. So V2 is equal to square root of 30 meters per second squared. Yeah, so we're gonna need divided by 1,000 here. Well, no, because we're doing V2, so we're gonna keep it. We're gonna keep it here. We're gonna do the 1,000 on the other side. So 2 times 320.29 minus 305.22. Now I had a question on office hours about the 1,000 too. This is given in kilojoules, and if you do the math on this one, meters per second, meter squared per second squared, that ends up being in joules per kilogram. So you got to take out the joule, you got to convert from joules to kilojoules. So in this case, we've got to multiply this one by 1,000, right? To get kilojoules, I'm sorry. So multiply this one to get from joules to kilojoules. So to get us to joules, okay? And of course this goes all the way across. Okay, and then so then V2 is then equal to 176.2 meters per second. Okay. All right, 1.76 meters per second. Okay, so that's pretty fast. That's some pretty high velocity air. Okay. Came in at 30 meters a second, and it leaves at 162. Man, it really had a lot of clog in that tube, and definitely had a situation there. But okay, fine. Dropped a lot of pressure, and we added some velocity. Okay, now problem. So part B is need to find the pressure. So we need to know the mass flow. So M2 equals m dot 1 by the first the mass conservation. Okay. And this is equal to A1V1 over V1 is equal to A2V velocity V2 over V2. And then essentially what we can do is we can cross off the areas because we said the tube is going to be constant area tube. And we can cross out, oh yeah, sorry, we have an R in here too because we have to have a, oh wait, let's get rid of that. Okay, so then now let's use the ideal gas law. So this is now equal to V1 P1 over RT1 equals V2 P2 over RT2. We can cross out the R's because we know that's constant. We don't know that anything else is constant, so we can just solve here for the pressure directly. Right, so then essentially using this mass flow equation, we can find, and the ideal gas law. So ideal gas law, substitute for the V's and you get that, okay? So that's how we're using ideal gas law in this case. If we had steam, do not use the ideal gas law, okay? Just don't do it, okay? For ideal gas, and it says ideal gas, use the ideal gas law. Okay, makes sense. So then we just solve this thing. So essentially P2 is equal to P1 V1 over V2 T1 over T2. Okay? And then we just put in our values here. So we were given that P1 equals 900 kPa by the problem. And then we have 30 meters per second over 176.2, which is what we found in part A. And we have 305 over 320. So you're bringing those back in again here. Okay, so now let's see. So then we solve this thing. We get P2 is equal to 146.1 kPa. And that's the answer. So the pressure has dropped, right? 900 kPa to 146. That's a serious pressure drop in an air pipe. That's a big restriction, essentially. So I don't know. We didn't have to actually solve for the area of the restriction. We just were given the problem boundary on each side of the control volume. So we didn't have to really know, but we know this is a pretty serious pressure drop. Let's say serious pressure drop. Okay, so that's good. I think I'm gonna quit here today because I don't want to go into system integration. So I'll just give you a little preview of what we're going to talk about. So here, system integration is the next thing we're going to talk about. And I guess maybe what I'll do on Friday lecture is I will go into detail on system integration and give us doing a couple examples of how we put all these systems together, how we define control volumes, and it's actually pretty important. So I think it's a good thing to do. And then the following, I guess on Monday, then I will go over unsteady problems, that is transient problems. Transient problems are tricky. So that's where this class starts to get tricky. And maybe I'll spend a day or so on that. So I guess with that, I'll quit for the day and post this lecture. So thank you for listening, and please, as I said, join office hours, write me email, let me know how things are going. If you like this format, if you don't, whatever, just let me know. Okay? Stay healthy, take care, and I will talk to you soon.